Bem-vindos de volta. Lembro-vos que este quinto e último encontro é o encerramento do plano com que a Fundação Francisco Manuel dos Santos decidiu assinalar os seus 10 anos de existência. 10 anos ao encontro dos portugueses. No encontro anterior, em setembro, questionávamos o futuro do planeta e acabámos por constatar de uma forma muito óbvia, com alguns dos maiores especialistas mundiais, que uma grande parte das respostas se encontra no oceano. Na altura questionávamos o futuro do planeta. O que vamos questionar aqui nesta última sessão é diferente. É o futuro da humanidade, não o futuro do planeta. Pode não ser preciso, no limite, tratar do planeta se não houver humanidade. Ou então, há ou não o risco ou a necessidade de virmos a ter de procurar um outro planeta e, afinal, nós, os terrestres, tornarmos-nos extraterrestres? Os convidados da última sessão de hoje são ambos físicos teóricos e questionam, e isto é a interpretação minha de uma forma muito senso comum, questionam as duas dimensões que alimentaram todo o trabalho científico de Albert Einstein e de muitos outros, por exemplo, o tempo e o espaço. Um deles, Michio Kaku, acredita que pode haver mais do que um universo. Mais do que um universo. Universos paralelos. Outro, Carlo Rovelli, procura a sua própria forma de explicar o tempo. E, minha sugestão, não lhe perguntem como eu fiz ontem, que horas são, porque a resposta pode ser longa. O que se vai seguir é uma verdadeira conversa cósmica. Please be welcome. Take your seats, please. Quem vai apresentar e moderar esta sessão é o professor Vítor Cardoso.
Vítor, tudo bom?
Bem-vindo. Um físico português que estuda o poder dos buracos negros. Professor, nice to meet you again. Please have a seat. Carlo.
Okay.
Vítor Cardoso é professor de Física no Instituto Superior Técnico e, entre muitas outras coisas, estudante, investigador de buracos negros, do poder dos buracos negros. É também professor visitante nas universidades de Amsterdão e de Tóquio, pelo menos. É o anfitrião desta conversa cósmica. Vítor.
Olá, obrigado a todos. É um prazer estar aqui convosco neste espaço fabuloso, num dia maravilhoso e a celebrar ciência num dia muito especial para todos nós. Obrigado por terem vindo. Eu agora vou mudar para inglês. 100 years ago, there was a now famous headline in the Times of London. It read, "Revolution in Science, Newtonian Ideas Overthrown." There was an eclipse in 1919, and scientists measured the deflection of light of distant stars as it passed close to the sun. And this very tiny deflection showed that the prediction that Newton's theory of gravity had was wrong. So Einstein's description of gravity finally triumphed, and with it a completely different understanding of the universe and of the cosmos. Time was no longer a fixed thing, something that you measured in one and every clock, was a plastic and elastic entity. Time is an illusion, Einstein said. Shortly after we started to understand the content of the field equations of Einstein's theory, we also understood that it contained the description of the universe itself. We were finally able to think about the universe. How does it look like? Is it expanding? Is it static? Just in terms of the mathematics of the Einstein's description. And when you think that you can understand something, then you get some responsibility for that thing. We have some responsibility for the cosmos. We need to understand where matter came from, where the universe is going, what exactly is governing the distance between the stars, how stars grow, how stars evolve, how galaxies die, right? 20 years ago, we knew already, of course, that the universe is expanding, but roughly 20 years ago, we realized that it's expanding at an ever-increasing rate. So the universe is getting colder as we speak. But today, we'll warm ourselves with our speakers, and we'll have some cosmic conversations, okay? Now, I was supposed to introduce them, but they're so famous, you can just Google them. Okay. But let me just tell you two curiosities about them. The first about Professor Michio Kaku. It's my pleasure really to be here sitting with him because the reason why I'm in physics, well, at least one of the reasons, is one of his books. When I was finishing high school, you know, the only book I ever carried along was one of Professor Kaku's books, so thank you. That's right. Of course, I still read Professor Rovelli's books whenever I need to give a talk or a course, because it's an amazing source of inspiration. And actually, I just learned that in Italy, his books are the most translated books ever, second only to Pinocchio. Amazing.
Thank you.
So, without any further ado, let's start our cosmic conversations with Professor Michio Kaku. Thank you so much.
Mm-hmm. Well, after such a great introduction, I can't wait to hear the speaker myself. First of all, let me say that I've had the privilege of interviewing over 300 of the world's top scientists for BBC television, the Discovery Channel, the Science Channel. And every time I interview these top scientists, I ask them the key question, the most fundamental question of all time. And that is there intelligent life on the Earth? Well, I was watching the Kardashians on TV last night. Nope, no intelligent life on this planet. But let me dedicate my comments today to the spirit of exploration of the Portuguese navigators who left Lisbon in the 1500s to give us the first realistic maps of the world. The Cape Canaveral. The Cape Canaveral of the 1500s was Lisbon. And the astronauts that braved unknown dangers were the Portuguese navigators of the 1500s. So I'd like to dedicate my comments for that. And let me also say that in the books that I've written, I've tried to explore the frontiers of science. Where is physics taking us? Into the realm of even science fiction. In my books, I talk about time travel. I talk about teleportation. I talk about artificial intelligence. I talk about what's out there in the universe. And in my other book, I talked about inner space. We physicists are exploring not just the universe, but the universe of the mind. With MRI charts, we were able to calculate the blood flow of the living brain to understand its secrets. For example, some of the darkest secrets of the brain we can now expose. For example, everyone believes, but no one could prove until now. Everyone believes that, well, when a man talks to a pretty girl, he starts to act stupid. Absolutely true. We have brain scanned men talking to pretty girls, and sure enough, blood drains from the prefrontal cortex, and they start to act mentally retarded. Absolutely true. And in my book, The Future of Humanity, I talk about the future of the space program. And where are we going to go throughout the universe? And that's a subject of today's lecture. But maybe one day we'll even encounter intelligent civilizations in space. You know, I'm on radio, and some people call me on radio, and they say, Professor, you're wrong. You're wrong. The aliens are not there. The aliens are here. And I ask them, how do you know that? And they say, I know that because I've been kidnapped, they say. I've been kidnapped. I've been in their flying saucers. Well, I have a word of advice. The next time you are kidnapped by a flying saucer, for God's sake, steal something. There's no law against stealing from an extraterrestrial civilization. No law whatsoever. You're not going to go to jail, and you'll have proof. And you'll have proof that, yes, you really were in that flying saucer. Well, today, let's talk about the space program, cosmology, the universe, and the world of Einstein. But first of all, some people ask a fundamental question. Why bother? Why do we want to go into outer space? Well, the dinosaurs did not have a space program. And that's why they're not here today. How come there are no dinosaurs here today? Because they did not have a space program. But we do have a space program. And every time I look at this picture, I say to myself, what are these dinosaurs thinking? One dinosaur is probably thinking, oh, this is going to really ruin my day. And the other dinosaur says, aw, shucks. Well, you see, the dinosaurs were wiped out not just by an asteroid or a comet, but the Earth faces threats all the time. In fact, on a scale of 5 billion years, the sun will eat up the Earth. Either we leave, adapt, or die. That's a law of physics, practically. 5 billion years from now, we will have the last nice day. The sky will be on fire, the oceans will boil, the mountains will melt, and we will go back into the sun. You know, the Bible says, from dust to dust, ashes to ashes. We physicists say we came from stardust, and we will go back to stardust. And that's not the only danger facing us. Supervolcanoes, ice ages. Did you know that 99.9% of all species on the Earth go extinct? Extinction is the norm for life on the Earth. We think of Mother Nature as being warm and cuddly. Yes, Mother Nature can be warm and cuddly, but every once in a while, nature gets bored with us and wipes out 99% of all life forms on the planet Earth. If you don't believe me, dig underneath your feet, and you will find the bones, the fossils of the 99.9% of life forms that are now extinct. But you see, we're different. We have a space program. The first era of exploration was in the 1960s, but it was not sustainable because of cost. You realize that in 1966, the moon program cost 5% of the United States federal budget. 5% of every dollar you paid in income tax went to the moon program. That's unsustainable. And that's why now we're entering the second golden era of space exploration. And who's leading the charge? Believe it or not, billionaires are leading the charge. Elon Musk is putting his checkbook where his money, where his mouth is, and helping to bankroll a new fleet of rockets. The Falcon Heavy here even launched a sports car into outer space, something that only a billionaire would do. And NASA, not too far behind, is also preparing for its moon rockets. In the next 2 to 3 years, we're going back to the moon. Astronauts will then land on the moon in mid-decade, and after that, we're going on to Mars. In fact, we're going to have a traffic jam around Mars. and the moon. Who's going to the moon? NASA is going to the moon. SpaceX is going to the moon. Blue Origins, the spin-off of Amazon, they're going to the moon. The Chinese are going to the moon. We're going to have a traffic jam around the moon, and I personally think that our descendants, we don't know when, but our descendants will probably honeymoon on the moon. And now we have the BFR, the world's biggest rocket. And Elon Musk has said that he wants 1,000 of these to create a colony on Mars over the next 20 years' time. Some people think that time frame could be a little bit accelerated, but look, as long as he's paying for his money with his space program, I say, sure, go ahead, I'm not paying for it. This is the BFR, the world's biggest rocket. B stands for big. R stands for rocket. And you know what F stands for. And yes, we've talked about Mars, we've talked about Europa, we've talked about Enceladus, but what's even beyond that? We've now discovered 4,000 exoplanets orbiting other stars, and we now realize we can take a census of the Milky Way galaxy, a census of the galaxy. We now know that, on average, every star you see tonight has a planet going around it. That is astounding. How many planets are Earth-size in the Milky Way galaxy? Billions. And we're now looking for the Holy Grail. The Holy Grail of planetary science is to find a twin, not a super Earth, but a twin of the Earth in outer space. A twin with liquid water oceans, perhaps with oxygen, perhaps in the so-called Goldilocks zone of being just right from the mother star. Yes, we hope one day to find a twin of the Earth in outer space. And what are we going to do about it? Well, we hope to visit it. My late colleague, Stephen Hawking, liked the idea of sending chips into outer space to reach the nearby stars. This is the Breakthrough Starshot program using laser beams to energize a fleet of chips to reach Alpha Centauri within 20 years' time. It'll go up to 20% the speed of light. So we're now talking about reaching the nearby stars with known technology, reaching Alpha Centauri. And in the Alpha Centauri system, we have Proxima Centauri b. It is an Earth-like planet, only 4 light years from the Earth. That's a hop, skip, and a jump. And beyond that, we're now talking science fiction. It turns out that in France, we're building the ITER fusion reactor. A fusion reactor that'll take a piece of the sun and energize machines on the planet Earth. And what is the fuel for a fusion reactor? Seawater. Hydrogen from seawater can be burned to give you energy the same way the sun gives us fusion power and lights up our world. Well, why not build a fusion rocket? We physicists have done the math, and yes, the fusion rocket would be much larger than the Saturn rocket here, but it could conceivably reach 50% the speed of light. The design that I like best, coming from science fiction, is the ramjet fusion engine. It is an engine that needs no fuel whatsoever. It looks like an ice cream cone. It scoops up hydrogen from interstellar space in the forward direction, burns it in a fusion reactor, and then can approach light speed all for free. It does not require any fueling whatsoever. It simply scoops up interstellar hydrogen, burns it in a fusion reactor. And then, of course, if you're a fan of Star Trek, you want antimatter rockets. Antimatter is the ultimate source of energy in the universe, 100% conversion of matter into energy if you could build a rocket that has antimatter as its basic fuel. The problem? Well, it would bankrupt the planet Earth to do this. Small detail. But this rocket here is the ultimate rocket capable of reaching the stars. And then I have my own personal point of view. My own personal pet project is something I call laser porting. You see, one day we will digitize you. Everything known about you will be digitized. Silicon Valley is already offering for money the digitization of your parents. Most people have no memorabilia from their parents, maybe a wristwatch, maybe a photograph of your parents. Why not have your parents digitized so you have them always? One day we might be digitized. We'll become immortal. All your memories, personality, all your traits can be digitized so that you can have a conversation with your great-great-great-great-great-grandchildren and live forever. This is called the Connectome Project, where we're digitizing the human brain itself. You know, just a few months ago, it was announced that we can now digitize the brain of a fruit fly. Every single neuron of a fruit fly can be located, put in a computer, and we can, in some sense, simulate the brain of a fruit fly. Now, our brain has 100 billion neurons, a lot more than a fruit fly. But one day we will digitize the human brain. And what are we going to do with it? I say, shoot it into outer space. Put it on a laser beam and shoot it to the moon. How long would it take for you to go to the moon? 1 second. To go to Mars, how long would it take for you to go to Mars? 20 minutes. To visit Pluto, maybe 8 hours. In other words, you could have breakfast in New York, where I live. At brunch time, 10 o'clock, you can be on Mars. Visit Saturn and Jupiter in the afternoon. Visit a few asteroids after that, and come back to the Earth with no problems whatsoever, with known technology. You see, on the moon, there would be a mainframe that downloads your information of your laser beam, downloads the information, and puts you into an avatar. The avatar is superhuman. Looks just like you, except it is super strong, super beautiful, super whatever. And you can then roam the universe in a superhuman body without having to breathe the poisonous atmosphere with any gravitational field, explore the universe. Now, let me stick my neck out. I think that this already exists. I think aliens from outer space, they're way past booster rockets. They're way past accidents. They're way past weightlessness. They don't bother with that. They simply digitize their soul and send their soul on a superhighway and explore the galaxy at the speed of light. In fact, this could already exist. Next to the Earth, I'm of course speculating, next to the Earth there could be a superhighway containing all the digitized souls of alien life, and we are too stupid to know it. How would we even know it? And then, of course, what lies beyond that is the mystery of creation and black holes. This is a picture, the world's first picture of a black hole, taken by lashing together the information from several radio telescopes. It is so powerful that it can detect an orange sitting on the moon from the planet Earth. This is a black hole. And then the question that even children ask is, what's on the other side of a black hole? Now, the short answer is, I don't know. But if you take Einstein's equations and simply solve them for a spinning black hole, you find something very interesting. In 1963, mathematician Roy Kerr from New Zealand solved Einstein's equation for a spinning black hole. And he found that black holes do not collapse to a dot, they collapse to a ring of fire. And if you fall through the ring, you don't die at all, but you wind up in a parallel universe. And if you go through the ring a second time, you wind up on a second parallel universe. Now this, of course, is pure mathematics. What we have to do is quantize this. And this is then what I do for a living. When you quantize it, then we can ask the question of how stable is this object? Now, my colleague Stephen Hawking looked at this very carefully. And he said, first, you need positive energy to open the gateway, according to Einstein's equation, according to what is called the Kerr metric. Then you need negative matter, or negative energy to stabilize it so it doesn't crush you when you go through it. And is it possible to actually go through the wormhole? Well, Stephen thought, yeah. Time travel, he thought, would be difficult, but wormhole travel seemed to obey the known laws of physics. But we'll have to await until we can calculate quantum corrections to see whether stable this is. Now, you've seen this before. Where in English literature have you seen wormholes before? In Alice in Wonderland. Alice in Wonderland was written by Charles Dodgson, not Lewis Carroll. Lewis Carroll was a pen name. Charles Dodgson was a professor of mathematics at Oxford University. He could not publish a children's book under his name, so he created a pseudonym, but he realized that in mathematics we have something called multiply connected spaces. Charles Dodgson realized that if I take two sheets of paper, put them parallel to each other, and stick a hole through both, you have now connected two sheets with a parallel universe. In other words, wormholes could become shortcuts through space and time. As I said before, it would be ridiculously hard to build one of these things. Positive energy, like a black hole, negative energy to stabilize it. It is beyond anything that we can conceive of, but it may be possible that, who knows, alien civilizations in outer space may have already done so. You see, the known laws of physics break down at something called the Planck energy. 10 to the 19 billion electron volts is where everything we know about physics breaks down. And in principle, if you could heat vacuum to the Planck energy, 10 to the 19 billion electron volts, space would start to boil. You could begin to boil empty space. Bubbles will form. Bubbles. And if you fall through the bubble, perhaps you wind up in a parallel universe, and perhaps that's the origin of the universe itself. There are many theories about the origin of the universe. One theory says that perhaps the universe is a white hole. On the other side of a black hole is a white hole, according to one theory. You fall into the black hole, and you get shot out the other end in a white hole. And doesn't that sound like the Big Bang? Well, quite frankly, we don't know what set off the Big Bang. But we do believe that you have to quantize the Big Bang. You have to apply the quantum theory to the Big Bang. And when you quantize an electron, for example, like in a transistor, the electron can be two places at the same time. That seems to violate common sense, right? But tough. That's the way the world is. Get used to it. So if the electron can be two places at the same time, why can't the universe be two places at the same time? In other words, the Big Bang itself perhaps had parallel universes. And how do we prove all these fantastic theories? Well, with a machine. We have built the Large Hadron Collider, a gigantic machine outside Geneva, Switzerland, to, in some sense, recreate a mini universe, to recreate some of the conditions of the Big Bang itself. 27 kilometers in circumference, the biggest machine of science ever conceived of, and we finally found the Higgs boson. And you may say to yourself, hooray, hooray, we found the Higgs boson. But then the question is, what does it all mean? Where is it all going? Well, folks, this is it. This is the end product of 12 billion euros, the end product of 20 Nobel Prizes that have gone into creating this. This is the theory of almost everything. It is called the Standard Model. It fits all the data. It is the end product of thousands of physicists working with one goal: to recreate conditions of the early universe. What's wrong with this? Well, nothing's wrong with it. The only problem, it is also the ugliest theory known to science. It has 36 quarks and antiquarks, 19 or more free parameters, 3 carbon copies of quarks and leptons and Yang-Mills particles. It is a theory that only a mother can love. This is it, folks. Billions of dollars to create the standard model. Can nature be this cruel to give us a theory like this? I like to think of it as getting a whale, a platypus, and an aardvark, scotch taping them together and saying this is nature's ultimate, finest evolutionary end product, the end product of a million years of evolution on the earth. Well, you see, this is not quite how Einstein thought it would progress. Let me say a few things about myself. When I was 8 years old, something happened which changed my life. It just turned my whole life upside down when I was 8 years old. When I was 8 years old, they announced that a great scientist had just died. And I still remember a picture. That evening's picture changed my life. That picture was a picture of his desk. And the caption said something like, "This is the unfinished manuscript of the greatest scientist of our time." So I said to myself, why couldn't he finish it? I mean, what's so hard that a great scientist couldn't finish it? Why didn't he ask his mother? It's a homework problem, right? So I went to the library and I found out that this man was Albert Einstein. And that manuscript that I saw on the evening news was the unfinished theory of everything. He wanted an equation no more than 1 inch long that would, quote, allow us to read the mind of God. And for the last 30 years of his life, he chased after a theory which would unite all the laws of physics into a single theory, perhaps no more than 1 inch long. I've read his memoirs, I've read his book, The Unfinished Manuscript, and he keeps saying, I'm missing something. I'm missing a principle. I'm missing a paradigm. What does it all mean? How are we going to fit everything together? Well, there is a paradigm that could, in fact, unite everything. And that paradigm is rich enough to understand the entire standard model. And that paradigm is music. 2,000 years ago, the great mathematician Pythagoras wondered, what is music? And he took a lyre string, and he said, well, the lyre string beats at certain frequencies, discrete frequencies. And he said, aha, that is music. And that is the beginning of what is called string theory. We're talking about the fact that music is the only paradigm rich enough, complex enough, sophisticated enough to explain everything. Well, today we believe, though we cannot prove, very difficult to prove any of these theories, that subatomic particles are nothing but notes on a tiny rubber band. And when the rubber band vibrates this way, it's called an electron. When the rubber band vibrates this way, it's called a quark. And how many vibrations are there? An infinite number of vibrations. So what are the subatomic particles of the standard model? Nothing but notes on a violin string. What is physics? Physics is the harmonies we can write on vibrating strings. What is chemistry? Chemistry is the melodies we can play on interacting vibrating strings. What is the universe? The universe is a symphony of strings. And then what is the mind of God? The mind of God, according to this theory, is cosmic music resonating through hyperspace. That is the mind of God. Now you may say to yourself, well, all that's nice and good, but how does that stack up against the data? It turns out that the standard model with 36 quarks, 19 free parameters, 3 generations of particles are predicted by string theory. Music, the music of Einstein, the music of the quantum, are nothing but different notes on a vibrating string. So what's the catch? There's always a catch. The catch is, this theory is so successful, it predicts other universes. It predicts a melody of infinite number of parallel universes. There's a new paradigm coming out. Not everyone likes this, but let me explain what it is. Our universe is a bubble. We live on the skin of the bubble, and the bubble's expanding. That's called the Big Bang Theory. But string theory is a quantum theory. Therefore, it can be 2 places at the same time, which means that we have a bubble bath of parallel universes. And so when these 2 bubbles collide, or when these bubbles fission in half to create a baby bubble, that's the Big Bang. So what is the Big Bang? The Big Bang is nothing but the collision of universes, or the peeling off of a baby universe from another universe. And what are we going to do with this? We're going to test it. The next particle to be discovered by the Large Hadron Collider, we hope, is the photino. It is a particle which is neutral, stable, and massive, and we hope it makes up dark matter. Dark matter is what holds the Milky Way galaxy together. It is invisible, and we hope to find the particles that make up dark matter in the Large Hadron Collider, or the next generation of machines beyond the Large Hadron Collider. Already, the Japanese, the Chinese, and the Europeans are now bidding to create the next accelerator beyond the Large Hadron Collider. And from that, we hope to answer some of the deepest secrets of creation, like the universe. Is it possible to create a baby universe? Is it possible to be a god? And in some sense, one day, if you can harness this cosmic power, manipulate space and time itself. Well, I'm running out of time, so let me say 2 things. First, some of you have my books. I'd be more than happy to sign your book after my talk. And after I sign your book, you can go to eBay and auction them off for money. Yes, you can make money on today's talk. And second of all, let me say a few things about myself. You see, when I was a child, I had a role model. That role model was Albert Einstein. Let me tell you my favorite Einstein story. When Einstein was an old man, he was tired of giving the same talk over and over again. So one day his chauffeur came up to him, and the chauffeur said, "Professor, I'm really a part-time actor. I've heard your speech so many times, I've memorized it. So why don't we switch places? I will put on a mustache. I'll put on a wig. I will be the great Einstein. You can take my jacket and be my chauffeur." Well, Einstein loved the joke, so they switched places. This went along famously until one day, a mathematician in the back asked a very difficult question. And Einstein thought, oh, the game is up. But then the chauffeur said, "That question is so elementary that even my chauffeur here can answer it for you." Thank you very much. Thank you.
Wonderful. Thank you so much, Michio. The clock is ticking, but there's still time to talk about time. So let's hear Professor Rovelli.
Thank you very much. Thank you all of you for being here. It's a pleasure. Thank you, Vítor. I was in Lisbon this summer for a month visiting Vítor research group. He works in gravity, similar to me, and it's a pleasure to be here. It's a difficulty to talk about Professor Kaku, of course. He's a great speaker. But let me say something. I belong to a different kind of scientists. I don't believe in string theory. I don't believe in multi-universes. I don't believe in going faster than light in the galaxy, sending our mind there. I also think that science is fantastic, is beautiful, but it has a lot of limitations. We humans are not so powerful, and science needs a sort of humility and recognizing our own limits. That's the way I think we can best address the difficulties, which I agree with Professor Kaku are there and are in front of us. So, in this spirit, I'm not going to talk too much about speculations. What could it be? Are the universe or strings or things like that? I speculate. My science, it's a lot speculation about how the world could be. But I think it's essential to keep very, very clear the things we have learned, which are remarkable about the universe, separated from our attempt to look more far away. Science lives at the boundary between what we know and what we don't know, and it has to step in what we don't know. But at the same time, especially in communicating to the large public, should be very clear what is known and what is not known. I'm going to talk about time. I will use this 27 minutes to talk about time, and not to tell you everything we know about time, because there isn't time for that, but tell you a few things which I think are amazing about what we have discovered about time, and also what we think might be true about time. So let me start by saying that time is interesting. And you may say, oh, wait a moment, time is something we all know what it is, right? This is the now, and then time passes. We are in one instant, then there's another instant. So we have a clear idea of what time is. Right? Time is this long sequence of instances. And I have a metaphor for time. Time is this long line that passes, that goes from a very far away past all the way to a very far away future. I'm just tie it here. And let's see if I can make a knot. My first article was about knots and quantum gravity, so I should be able to write a knot. Okay. So we are here at some time. Let me bring the now here. This is a now. This is before, this is even before, this is yesterday, a month ago, the Big Bang. Who knows, maybe before the Big Bang, we don't know. This is tomorrow, after. So this long line is our metaphor of time, this way of thinking of time. That's the past, that's the future. They're completely different. The past is fixed, we remember it. We have pictures about us in the past. We don't have picture about us in the future. Future is open. We don't know what's going to happen. We know what happened in the past. Time passes, so this I have to move it because time has passed a little bit, right? Between one point and the other, say between the beginning of my talk and the end of my talk, there's half an hour. So clocks measure half an hour between this event and this event. Every clock would measure half an hour. This is really half an hour between two instants. And at each instant, so now, we are in the same now, right? In this instant, we are together in the same now. And somebody in the moon, somebody on Mars, somebody in a different galaxy, we are all in the same now. So time is pretty clear. Almost everything I've said is wrong. Is factually wrong. Wrong in the same sense in which if I say the Earth is flat, it's wrong. If I say the Earth does not move, it's the sun which is moving around us, that's wrong. That's factually wrong. Of course, the Earth is roughly flat. If you take a map of Portugal, it's roughly flat, right? So to some approximation is okay. And if we just look at our relative motions here, we can say, well, this Earth is not moving, I'm moving with respect to the Earth, that's also okay. So this picture of time I gave, it's good, but it's a picture of time which is only good for us in our daily life. As soon as we look far away in the stars or in the small, in this powers of 10 that this afternoon started from, as soon as we go to larger scale or smaller scale, this picture of time goes wrong, completely wrong. And I want to tell you why. And it's very simple, and I'm giving you 2 or 3 elements of why. And the first 2 or 3 are well-established science, and then I will go more and more toward speculations. Let me make the first fact that makes this picture wrong. The fact is super simple, is the following. Take 2 clocks, okay? And imagine that they were very good clocks, better than these 2. These are good clocks, these are good watches, but not. Today we have watches that measure time with a precision in 1 to 10 to the 15. So they miss a second every, millions of billions of seconds. So they're super precise. So we take a very good clock and you raise one. You wait a little bit, 1, 2, 3, 4, 5, 6, okay? And then come back. They don't indicate the same time. They indicate the same time to start from. Wait, raise, come back. They indicate a different time. So up here, and I really mean 1 meter, we can do this experiment in laboratories today at a meter of altitude difference. Up here, there's more time than down here. It's not just clocks. If you live up there, you live longer. You have more time to think. Flowers have more time to blossom. Pendulum has more time to pendule, and so on. So there is really more time there than down. Your head lives longer than your feet, unless you live upside down. This is a fact, and you say, how is it possible? Well, you just measure it, and it turns out to be true. What is spectacular is that Einstein predicted that much longer before having clocks good enough to measure it, but it's a reality. So this means that between 2 points here and here, the amount of time is not fixed. It depends whether you're up or down. Now, why we don't see this usually? Because the effect is very small. You need a very, very precise clock to see it. But the effect is very small here on Earth. If you go, Jupiter is already stronger. If you go near a heavy star, it's even stronger. If you're near a black hole, clocks is almost stop. They slow down enormously when you go near the black hole. And in some speculative models in which we are studying today, in many groups, including my group in Marseille, if you go inside a black hole and you wait long enough for quantum effect to happen, you may come out. But you can go in and come out after a fraction of a second in your clock, in your time, while outside in the universe, billions of years have passed. So it might be that a black hole is actually a shortcut to the future. It might be, we don't know. But we know for sure that time has this extraordinary elasticity. So this line is just a bad metaphor for time. From here to there may be 1,000 years for somebody and a very short time for somebody else. That's the first point. Second point, why this is wrong. And this is also something we have understood very, very well. Einstein has understood very, very well. But in my opinion, this is the most striking discovery of modern physics. So let me try to present in this way. What do we mean by now? I said we are all in the same now. Well, you see me, right? You see me, I am now. And I see you, sort of, because of this light, but I do see you, as you are now. Do we? Think for a moment. If you see me there, it means that light has moved from me to you up there. Now, light is very, very fast, but it's not infinitely fast. It takes a little bit of time. So when you look at me, you see me a few nanoseconds later. It takes maybe 100 nanoseconds to get to the end of the hole. So you see me how I was 100 nanoseconds before you're looking at me. And I see you how you were 100 nanoseconds after the moment I'm seeing you. So we're not looking at one another in the same moment. Now, of course, our brain resolves maybe a tenth of a second, maybe a hundredth of a second if you're a musician and you listen to rhythm very, very carefully. But this is much, much longer than the time lights take to go back and forth. So it's irrelevant. the time light takes to go back and forth, we don't perceive it. It's almost nothing for our mind. So we say we are just in the same now, but we aren't. There is this discrepancy. But now, I was 12 when humanity got to the moon. I remember, I don't know if you have heard the conversations between Cape Canaveral and the astronaut on the moon. How is it going? It's going very well. Okay? There was a time delay for light or radio signals to go back and forth. And if we go to Mars, which I hope it will be maybe 15 minutes or half an hour, depending where Mars is with respect to us in the solar system, for signals to go back and forth. So we cannot say right now on Mars because we see it, because anything we see on Mars is 15 minutes earlier. Now it turns out, and I'm not going through the detail, that if you fold together the fact that clocks go at different speed and the fact that light takes time and so on and so forth, careful, it is impossible to give meaning to saying at the same time at long distances. On Mars, we can say that there's something happening in the future, which is after a signal goes there, something happening in the past, so before I could see something there. But in between, there is a lapse of time on Mars, which is half an hour, which is neither future nor past for us, and they're equally present to us. So the very idea that there is a single present all over the universe is just not compatible with the way the universe is worked, with the way reality is made. There is no present in the universe. There is no sense whatsoever in asking what happened today on a distant galaxy in Andromeda. So the very notion of present now, it's an approximation which we use of talking to one another because we are close enough and we don't resolve small intervals of time. The present is an approximation. There is no present in the real temporal structure of reality at large. This is mind-blowing. It is something we know for sure. 2. 3. And a little bit more time has passed here. 3 is another extraordinary discovery of physics. In fact, it's a step, and it's something we know quite well up to a certain point, and then we are confused. It is the following. One of the things I said when I said we all know what is time is that the past is fixed and the future is open. We remember the past, we don't remember the future. That seemed to be plain and obvious. But something happened in the development of scientific knowledge, which is the following. We have been able to write the basic equation that describe what happens to all things. Light, atoms, everything which is around us. And those equations don't distinguish the past from the future. So this was a striking contradiction with our experience. The Newton equation, the Einstein equation, the Schrödinger equation, the equation of quantum field theory, future and past are the same, but in our experience, future and past are different. Where does the difference come from? Well, there is one equation which distinguishes the past from the future, and it has to do with heat, temperature, warm and cold, hot and cold things. And that's a well-known equation is the second law of thermodynamics, which says that entropy grows. Entropy is roughly heat divided by temperature, something like that. So there's a certain quantity that grows to the future and decreases toward the past. All right, so there is one equation that breaks the difference between the past and the future. Well, yes and no. Why? Because this equation says that there's a difference between the past and the future only when there is heat, which actually is true. If you think for a moment, let's see, if you have a pendulum, say it's a pendulum, something that pendulum, well this is doesn't, pendulum, okay, if you have a pendulum and you make a movie, and you show the movie backward, you see also a pendulum. There's no heat here. But if you wait for a while and this slows down, you show the movie backward, you see something funny. This starts moving by itself. And if it slows down, it's because there is friction, there is heat the energy goes into temperature, into heat. So every time there's a difference between past and future, there is heat. But what is heat? In the 19th century, Boltzmann and other people, Maxwell, understood, and I think you know that heat is nothing else than the fast movement of molecules. Heat is not a thing, it's just how things move. So the difference between a glass of water, hot and cold, is just that in the hot one, the molecules go very fast, in the cold one, they go slowly. But wait a moment. If heat is nothing else than movement, and the laws of movement don't distinguish the past from the future, how come that heat distinguishes the past from the future? Something funny here. Something very funny. And that's not entirely clear today. There's a part of the story which is clear, which is that the difference between the past and the future is that going toward the future, the energy gets dispersed into heat. So it's a sort of disordering of things. Instead of a single variable moving, the energy goes into all the variables. So it's just disordering. That's clear. So it's clear why things get disordered. But why the other way around? They were ordered. Who ordered the universe at the beginning? Or in technical terms, why the entropy of the universe was low to start with? We don't know. I think I've speculated, and this is a speculation, that this difference between the past and future comes not from the microphysics, but from the macrophysics, from the fact that we don't look at the individual molecules, and therefore we depend on the perspective on which we look at things. But this is mind-blowing, because it means in some sense that the difference between the past and the future depend on the way we interact with the universe. The universe by itself, if we look at all the degrees of freedom, is not going in one particular direction. It's our interaction with the universe that chooses one possibility. We look at the universe in such a way that the entropy was low at the beginning. Are we sure of that? No, we are not. But there is something totally mysterious today, and there is conferences of physicists and philosophers who ask why the entropy was low at the beginning, why the past is different from the future, why we remember the past and not the future. It's an open question. Let me step one more into the unknown. As Professor Kaku was saying, we don't yet have a quantum theory of gravity. And he has been working on it, he has been contributing a lot to string theory. I've been working on it. This has been the main interest of my life, to write a quantum theory of gravity. I work in a theory called loop quantum gravity. Once you take the equations of Einstein general relativity and you try to merge it with quantum mechanics, once you try to bring together quantum and Einstein understanding about space and time, something remarkable happen. You're looking at very, very short scale. The movie of the powers of 10 went up to scale of the cosmos and then down to the nuclei of the atoms. You have to go something like 15 more steps down, 15 more powers of 10 down to small, to get to when quantum gravity is relevant. And down there is a sense in which time disappears entirely. What does it mean, disappear entirely? It means that in the equations we have, in the theory in which I'm working, which is loop quantum gravity, you look at this equation, there is no time variable t at all. What does it mean? It means that there are variables corresponding to the handle of the clock. There is a variable corresponding to this clock. There is a variable corresponding to this other clock. There is a variable corresponding to where is the sun, where are the things. And the theory describes how these variables change one with respect to the other without a single time variable that orders things. So it's not that nothing changes. Things change. The theory describes change. But the change is not ordered in a common dancing time. See, I think the universe is not like a director of orchestra that gives the common music to everything, common rhythm to everything. It's just things happening separately and interacting the one with the other. There is no time, even locally, as we think it usually, in the extremely small scale of reality. So we don't know. We don't have a quantum theory of gravity yet. Or actually, we do have quantum theories of gravities, but we need to test them, and none of those have been tested, so we're not sure. But there is a certain consensus that something extremely funny happens to both space and time when you go to very, very short scale. And in several theories, you just lose completely a time variable when you go down there. So I listed clocks go at different speed depending on where you are. The present is an ill-defined notion if you look at the universe at large. The difference from the past to the future is only there if there is heat, and comes from the fact that we don't look at the microphysics, all the possible motions of the individual molecules, but with only averages. And when you do quantum gravity, you lose entirely the t variable, the variable time, in the fundamental equations of the universe. So, you see, in a sense, time is layered. The more we understand better, the more we lose pieces of time. Or if you want the other way around, if you start from reality at the basic scale, which we don't understand very well yet, and you want to understand what is the time of our experience, you have to build up step by step. And the time of our experience is is a complicated structure which depend on many approximations. And I think that if we really want to understand time, simple physics is not sufficient. Not because there is something non-physical in the world, but because we are very complex systems ourselves. And to understand temporality in full, we need to look at this complexity. Caroline Pork was saying what characterizes life is complexity, and what characterizes us thinking mammals with this brain, it's an enormous complexity in the way we interact with reality in our brain. We have a feeling of time passing, very clear and very strong. Time is not something remote to us. It's something directly connected to our experience. We cannot even think at ourselves outside time. But this is not into physics. Physics is just a handle of a watch that moves. This is because we have memories of the past. We have anticipations of the future. So when you guys think about time, what you're really thinking about is the memories and the anticipations. But stones have no memory in the sense that we have memories. We have part of our brain, we are here, and we have part of our brain which is connected with what happened yesterday. I remember my father, I remember my grandfather. He's here, still there. So when I think about time, I think about these memories. I think what I'm going to do tomorrow. Tomorrow I'm taking a plane, I'm going to France, I'm going to London, to Cambridge. So for me, time is this memory, this anticipation, this window into the complex structure of reality, which is opened by my memories and my anticipations. But that is something real, but that depends on the specific structure of my brain. I shouldn't look for these memories and anticipation in the equation of physics, because it comes from a complicated physical thing. And it's more than that. And that's the last thing I want to say. Time interests us. Time is a topic that raises. My last book is about time, and I keep getting people asking me about time. And in fact, my entire work has been fascinated by time. Why? Because time touches us directly, very, very directly. Time touches us emotionally. Time is what brings us things, but also what causes us losing things. we're going to lose things in time. With time, we're going to lose our parents, our friends, ourselves. We're going to die. Time is not emotionally amorphous for us. Time is very emotionally charged for us. And if you look at the philosophers, even very different philosophers, they all have stressed this emotional aspect of time. And if you're a physicist, you may first think, wait a moment, if I want to understand time, I have to take all this away, because we physicists are not supposed to look at the emotional aspect of things. But I think if we want to understand what is temporality in all its complexity, which goes from the quantum gravitational aspect to relativity, Einstein idea, thermodynamics, heat, and so on and so forth, memory, entropy, if we want to connect to our experience of time, we cannot take away what time means for us. And for us, time is emotionally charged. And I think we make a mistake if we try to discard this as illusory, because it's real for us, but we also make a mistake if we try to look into basic equation of physics, something which doesn't depend on our basic equation of physics, depend on our emotions. So I think that the emotion of time, the Buddhists say that life is sufferance, and the reason life is sufferance is because you lose things, because everything is impermanent, and impermanence is a passage of time. So the core of a human experience is temporality in the good and in the bad. So this is to a large extent what time is for us. The emotion of time is not a fog that prevents us from understanding the complex structure of time. It's just one layer of this very, very complicated thing, which is the temporal structure of the world, and it, to a large extent, the emotion of time is what time is for us. Thank you. Should I take away the...
No.
Thank you.
Actually, what a fantastic exposition. We're now here. Somewhere here, we still have up to here to discuss a little bit. You know, a few months ago, I tried to have this conversation with my landlord. I was telling him, time is very relative. It depends. No way, man. It's a month overdue. Pay me the rent. So I would like to ask you, as theoretical physicists trying to unify interactions, something that's been an open problem, I think, for all of us, which is the lack of progress. We know the basic ingredients of physics, the fundamental interactions. We think we have a good description of gravity at all scales. GR is still general relativity, the theory that Einstein formulated more than 100 years ago, is still perfectly valid. And when I was coming to, actually in high school or college, all the buzz was about string theory. This will be the new thing. This will solve all our problems. And yet, it's been decades, and I sense there's a lack of progress. Do you have any thoughts on this, Michio?
That's the subject of my next book, is the fact that progress has been slow. But you see, we are humans. We expect immediate results for everything. We say hype, and we say, okay, where's the beef? I want the results now. But you see, science is not done that way. Science sometimes takes time. Look at Democritus' theory of the atom. That took 2,000 years for us to finally verify something that Democritus said. And we get impatient. Now, we hope to build a successor to the Large Hadron Collider. And we hope to put satellites in orbit that measure gravity waves. And so we expect to get vibrations from the instant of creation itself.
That's correct, but are there predictions from string theory that we can test?
Well, one prediction is dark matter, that it predicts that dark matter is the next octave of the string. We are the lowest octave. What is Einstein's theory? What is the standard model? just the lowest octave of the string. But the string is higher octaves, and they're testable. And that's why we want to find dark matter in the laboratory with the Large Hadron Collider, and that would clinch it right there.
I see. So, but Carlo, you have been working on an alternative to string theory. Do you think that the next decades will bring data that we can use to test against, say, loop quantum gravity, and that we can have the two theories talking to one another?
I think that we already are getting some enormously interesting data, which are new, which we didn't know in the past. 2 examples or 3 examples are the following. The large majority of people working either in string theory and related field that I know expected very strongly supersymmetry to show up at CERN with the LHC, with the current instrument, and it did not. It has been a big blow for the community, and somebody has talked even of the crisis of physics. I don't think it's a crisis of physics at all. It's good when we get information from nature. That has been unexpected information. Many people expected supersymmetric particles to be seen, and they were not seen.
Right.
I think we should listen. Certainly it takes a long time, and in the middle of the thing you're always confused. I mean, there were times in which Maxwell had already written down his equation, but it was not at all clear whether they were right or not. Dark matter is certainly one of the big mysteries around. It's going to be a source of our next...
So I guess my question is it depressing if 100 years from now we're still discussing only GR and the standard interactions that we know now? Is it depressing that we're just testing to finer details what we think are the basic ingredients, or is it the way that science must do?
I think things are changing. I mean, we have learned that. We have learned, for instance, that with the gravitational waves, that the electromagnetic gravitational waves go at the same speed, which has eliminated a large number of alternative theories. That's another new input. So nature is talking. And I think that some fashion will go down, some other will go up, and we'll learn. It has always been like that. It is true that we have, it doesn't seem much progress since the standard model of general relativity, but this is because those generations have been super good.
That's true. Yes.
The next big project could be LISA, the Laser Interferometry Space Antenna. The European Space Agency, NASA, is working on it. And we hope to get baby pictures of the instant of creation within a trillionth of a second after the instant of creation, not 300,000 years after the Big Bang, but the instant of the Big Bang. And we hope to find evidence of an umbilical cord, that if the infant universe emerges from the womb, maybe we can find evidence of an umbilical cord. An umbilical cord connecting our baby universe to a parent universe.
That's a good point. And by the way, for the audience, Portugal is highly involved in the LISA.
In LISA.
Yeah.
LISA is one of the beautiful phenomena. This is putting in solar orbit 3 satellites to measure gravitational waves with like an antenna which is as long roughly as the orbit of the moon. It's a huge satellite.
Right. So I would like also to discuss with you something that's been on our mind for a few years now, which is there's, I think as Michio was discussing, there's all this information available to us, but I'm not exactly sure how the information is being managed using scientific methods. It's standard nowadays to hear people saying that the Earth is flat, that you don't need vaccines because they're bad for you. So somehow, all of us are scientists because we think the data is there, we can go on Wikipedia and we know what's going on. But in fact, men and women of science are still needed to digest the data. Do you have any sense of where we're going with this?
Well, realize that the internet does not modify human behavior. A certain fraction of the human race are criminals. A certain fraction of the human race are perpetual liars. And the internet simply magnifies their reach. But it doesn't outlaw them, In fact, in a democratic society, you want crazy ideas to proliferate because you never know where the correct idea comes from. But I think the Wild West of the internet is birth pangs. Just birth pangs of the internet, because the internet was originally a military weapon. Right. And that's why there's no policemen, there's no rules, it's just an open road, because that's how it was designed to fight a nuclear war. It's young, it's still a very young technology. And I think as time goes by, a lot of the Wild West will be eliminated or at least assuaged.
Do you share this view, Carlo?
Yes, I think that the internet created a lot of damage, but this because it's new, and we're going to learn a little bit to use it. I think scientists have a responsibility here. Everybody has a responsibility, but scientists have a responsibility of using it properly, in a sense, and distinguishing clearly what is known from our speculation, I think, will be helpful to scientists have to be reliable. Society needs competences. I want my town to build a bridge and have it done by an engineering that there is a consensus is a reliable one. I don't want to be the one who checks the calculations of how to do the...
But you want to make sure that the person building the bridge is...
I want to... I think a scientifically educated public should be able to distinguish the good from the bad, the nonsense from the... I don't think it's up to the public to decide which theory is correct, but it's up to the public to recognize where the competence is, and up to the politics to define where the competence... I think there is something wrong in the idea, now all information is out, so everybody decides. I don't know anything about biology, so I'm not going to decide which biological theory is right, of the creation of life, but I can recognize, I think I can recognize, I hope. I see that there is a problem in recognizing those who have some theories about the origin of life, which are interesting, credible, worth developing from nonsense.
Yeah, but so how do we do it? I mean, so how do you stop this bad democratization of science? Like, you know, I'm not going to get my kids vaccinated because it's bad for them. What do you do about it?
That's a very good case. I think that it's a case in which things went wrong. I mean, there's information that spread enormously for political interest, for cultural interest, for good faith of people getting confused, and somehow the importance of the vaccines was underestimated and interpreted. Not vaccinating a population is totally stupid. We're just doing harm to ourselves.
Right.
Well, you know, as Deng Xiaoping of China once said, when you open the window, a few flies come in. So you have to open the window. You have to let the breath of fresh ideas, good ideas, circulate in society. But yeah, you get a few flies coming in. Now the question is how you detect those flies. We're scientists, and we believe in things that are testable, falsifiable, and reproducible. So every time someone comes out with a theory, we have to challenge them. Where's the testing of it? Where's the reproducibility? Where's the falsifiability to this thing?
Right. But do you think we have been doing that work well?
No, I think that scientists, for the most part, are in their ivory tower, doing their own lab experiments, not engaging with the public, and challenging the public to have things that are testable, falsifiable, and reproducible, because otherwise the public cannot decide what is correct and what is not correct.
So actually, in relation to this, I read recently, I think maybe in Harper's or something, that 1/3, let me see the number, 1/3 of youngsters would prefer to become YouTubers or influencers, whatever there is, rather than an astronaut. What's going wrong, you know? So what can we do? Should we do something about it? Is it time to expand horizons again?
Well, I think the problem is science has been too successful. Because we have been successful, because we've gone to the moon, because we've gone to Mars, people say, ho-hum, been there, done that. Right. And people get bored, basically, because science is so successful. But that's why scientists have to come into the public debate. We have to then challenge when patently incorrect ideas are circulated because they can hurt people.
Right.
I mean, I don't mind if people talk about flying saucers because it's not going to hurt anyone. But when people start to talk about, the anti-vaccination movement and stuff like that, you're talking about people's lives at stake, people's future. At that point, scientists do have a responsibility to jump in.
That's right. Do you agree with this, Carlo?
100%, yes, 100%. I don't know what can be done. Certainly, I see in many societies, with respect to 30 years ago, a decrease in confidence in competence. The people have less. And look, I myself went through a crisis here because I spent my life telling my student, think with your own head, think by yourself, which is the good message. And I myself, I went against my teachers, I went my own way, I've been rebellious all my life. But then I see a lot of, if you go, do an exercise, go to the websites of those people who believe that the earth is flat, okay? They have a slogan, think for yourself, don't believe your teachers.
It's a good slogan.
Wait a moment, that was my slogan.
Yeah.
That's, there is something wrong here. I mean, maybe I'm only getting old, I'm an old guy, so I say, no. So I think people should get scientifically literate. People should think. You should. But at the same time, I repeat, we are not competent about everything. I think we do mistakes if we think that everybody can decide whether by himself whether the Earth is flat or wrong. It's not true. I mean, how do I know if the Earth is flat or wrong? I believe Vasco da Gama. I believe in Rodrigo Vespucci. I believe my history textbooks. It's a collective enterprise, and I think. It's not really everybody against everybody else in thinking. We have to collaborate in thinking. We have to trust one another. So we have to build a trust. It's like in politics. If we think that all goes well if we fight, everybody fights for himself, I think we go wrong and we make wars and disasters. If we think that we're a family, and of course we fought in families. Families are good, right? Because you fight with your brothers, but that's okay. But then you work together because of the common good. Right. So I think there is a sense of collaboration that is what humanity needs most, in my opinion.
So, one final question before we go on to have some questions from the audience. 4 years ago, roughly, we finally saw Einstein's messengers, the ripples in space-time, gravitational waves, and we have very strong evidence from black holes for the existence of black holes for the first time. Later, last year and this year, we finally imaged black holes, one at the center of our galaxy, another at the center of M87. What do you think is the next frontier to be explored?
Well, I think the next frontier is outer space, that all these instruments like LIGO, the gravity wave detector and stuff like that, will be in outer space. And I think the next big accelerator will not necessarily be CERN. The next big accelerator will be the Big Bang.
Yeah, but so LIGO saw a binary black hole merging, conforming GR. What will these new observations tell you that at least gets us excited?
Well, we physicists knew it was going to happen. If it didn't happen, we would have a heart attack.
That's true.
Okay? That's when all hell would break loose.
I would be happy. Something
so
different.
when we found the Higgs boson, most of us physicists said, ho-hum, we knew the Higgs boson was going to be there. We knew gravity waves were going to be there. Because if they weren't there, all hell would break loose. Yes. The foundation of modern physics would collapse.
But so, Carlo, do you think we will, in our lifetime, get observational data that tells you, oh, there's some effects of quantum gravity here?
Yeah.
I know.
Let me answer this. I think we should distinguish two different questions. One is the dream of a final equation for everything, the dream of the final theory. It's not a bad idea to look for it, but I think that we're very far from it, and I don't see evidence.
But do you think it exists? Do you think that the universe is governed by a single simple equation?
What do I know? I mean,
Maybe you had a secret.
No, look, if I had known it, you would have read my paper about it. There were good attempts, and string theory was a wonderful attempt, but I don't see evidence of having a single simple equation that give. I don't think we have an equation from which the 19 parameters of the standard model can be computed today. And a lot of extremely smart people have worked on that. However, I think that the problem of unification, single equation for everything, and the much more contained problem of understanding the quantum property of gravity are two separate problems. They're not necessarily mixed. Some people think maybe, I think they're very separated. I think that we have a chance to understand the quantum aspect of gravity by themselves, and we don't have an answer yet, but I hope before dying, I really hope so, I'm optimistic, of having measured a signal from an exploding black hole, a correction of the CMB, some indication that dark matter is primordial black hole at the end of their Hawking evaporation. Some of the phenomena which today are being studied in some theoretical laboratories, and there are people who say, look, the fast radio burst observed by the radio telescope might be an explosion of black hole, which is a quantum gravity phenomenon predicted by this theory. Has it happened yet? No. Do I hope it may happen in the next 10 years? Yes, I do.
Well, you know, Nobel laureate Steve Weinberg likes to look at it this way. For centuries, the ancient navigators talked about a North Pole. There was always this gap in the maps. All these maps of the ancient world had a huge missing chunk called the North Pole. Magnets would trace the North Pole. Navigators would look at the stars and say, yes, there must be a North Pole, but no one found it. It took centuries before Perry finally nailed down the North Pole. Now, today in physics, we have the same situation. On one sheet of paper, I can write down all the known laws of physics at a fundamental level. One sheet of paper. Einstein's equation is half an inch long. Maxwell's equation is half an inch long. The standard model is, most of the page. But in one page, I can summarize all that is known about the universe with no exceptions whatsoever. So I think that, it probably does come down to one equation, just as Einstein thought. An equation perhaps no more than 1 inch long.
I will wait for that. And now we're going. So I think we still have a few centimeters. So, so we'll now take questions from the audience. Do I need to throw this? Okay, 2 questions.
I presume I'm allowed to ask one?
Yeah, of course.
Okay, this is for you, Carlo. If I understood you correctly, if this quantum theory of gravity that you described is correct, the one where you said you go 15 orders of magnitude past the level of the nucleus, and at that small level, time disappears. Am I right to think that that means that the universe has been here forever? And it's always been here, it always will be here?
Yeah, thank you for this question, because it goes to the heart. The answer is no. And let me say more precisely why the answer is no. I think that physics is about describing change, motion, evolution. In fact, all of science is described. Biology is describing a process, not entities. We humans are processes. We don't understand biology in a single picture. We understand how it changes. And so is physics. Now, if you say the universe has been there forever, the imagination we are putting on that is a static thing with time that passes and nothing happens. It's the opposite. Everything happens. Physics is about the description of happening. There's nothing static in physics. So much so that if you go down to the scale of quantum gravity, the simplest intuition, Professor Kaku has an idea, it's a boiling thing. Everything is happening at the same time, not ordered in any common time. So my intuition is that we're as far away as possible for the idea of a block universe, a static thing, nothing happens. It's the other way around. It's an unordered happening of things that only get ordered when we look at larger scale and we see more and more ordered by averaging over. It's for the same reason for which quantum mechanical certainty become classical certainty. Right? Why? Because just the law of large numbers. We average of many fluctuations and then things seem perfectly solid when in the small they're bubbling.
I think we have one other question.
Sim, e pedi ao professor se não se importaria traduzir.
Sim.
A pergunta era para o Carlo. Segundo percebi, nas equações básicas da gravidade quântica, a variável tempo não existe. Então, em termos de conceito, como é que ela vai aparecer nas equações da física? Ou seja, as equações da física têm o tempo, quase todas. Se na gravidade quântica as equações básicas, a variável tempo não existe, como é que ele emerge para as equações que estão imediatamente acima?
Yes. It was very well translated, so I think I understand exactly the question. First of all, the fact that the t variable disappeared from the basic equation is something of the 60s. In 63, Wheeler and DeWitt wrote a tentative equations for quantum gravity. Today is called the Wheeler-DeWitt equation. Wheeler used to call it the DeWitt equation, and DeWitt used to call it the Wheeler equation. At some point, people get bored and just said, well, it's a Wheeler-DeWitt equation. And in this equation, there is no time. And there have been 30 years of discussion on what it means. And I think what it means now has been clarified. It is very simple. So let me make it super simple. I can say, this morning I woke up at 8 o'clock, I had breakfast at 9 o'clock, at 11 o'clock I had a phone call, at 2 o'clock I came here at the theater and so on. So everything is ordered in time. But I could also say, when the sun was there, I had breakfast. When this happened, this other thing happened. When the sun was there, I came here. So I could talk not of when things happen in time, but I could only talk about what happened to one thing when something happened at another thing. So I could talk of relative times. So if I wanted, I could just not talk about time, but only talk about relative variable. When this happened, this other thing happened. This is a possibility for us, but of course it's much more easy to order everything and call a variable that orders everything. But it's not a necessity. We could talk about the event of the world without ever mentioning time, just talking about the event and how they are related to one another. Now, what happened when you go to quantum gravity, in a sense, is that clocks becomes quantum, they jump all around, so you can still talk about relation between variables, but you cannot order all these events with a single time variable. So you lose the ordering factor, but your question is how do I gain the possibility of when I go at large scale? Well, very simple, because at large scale, all the various clocks, my clock, your clock, his clock, their clock, the clock which is telling us soon we have to finish, they all go almost at the same speed in the same manner. If you look carefully at the Planck scale, they don't. They just go back and forth. But with a good approximation, they all go together. So we call this collective, averaged, imprecise variable our common time.
So this conversation will continue in a parallel universe. But now we need to close. Let me first thank you for being here. This was an amazing interaction. Let me thank the Foundation because it's a truly unique event organized in a truly unique and special way. And finally, our speakers because they were just amazing.
Thank you.
Thank you. Thank you so much.
Thank you very much.
Thank you, Professor. Thank you so much.
Thank you. Thank you.
Penso que o meu já está aberto. Eu tiro a corda já, porque vai-me dar jeito para fazer isto. Sim, deixa estar, eu já tiro a corda. Portanto, nós estávamos onde é que estava o cascol? Onde é que está o agora? O que é que estará agora a acontecer em Júpiter, em primeiro lugar? O cascol estava aqui, não é? Portanto, este é o agora. Vou tentar dar aqui outra vez o nó à corda. Vamos lá ver se isto corre bem. Eu prometo que eu tinha prometido que só iria fazer um número de ilusionismo depois da intervenção final do Dr. Jaime Gama. Mas, se calhar, vou começar já por este pequeno ensaio. Nada na mão, nada na manga, está bem? Portanto, e um nó muito mal dado, que o meu primeiro livro não foi sobre nós. Bom, o cascol estava aqui, não é? Portanto, este aqui é o presente. Vamos imaginar, peço-vos que me acompanhem, se isto for, por exemplo, o meu timeline, a linha da minha vida, e se eu estou aqui, e pegando na analogia há pouco do professor Rovelli, aquilo será o meu passado e aquilo será o meu futuro, certo? Portanto, se o cascol passar para aqui, eu estarei em direção ao meu futuro. E, eventualmente, chegarei ao último nó. Mais tarde ou mais cedo, espero que mais tarde. Isto é o que nos diz o senso comum, certo? Uma das pessoas, eu decidi improvisar isto agora porque tenho mesmo que manter aqui alguma atenção e porque acredito verdadeiramente nisto, é de um dos pensadores que mais me influenciou para além do Einstein. Vale o que vale. Isto é verdade, mas não é verdade que nós façamos este percurso desta forma, do nosso passado para o nosso futuro. O que é mais certo é que nós façamos este percurso assim, caminhando de marcha atrás para o futuro. Porque nós só percebemos o que ele é depois de passarmos por ele, porque a nossa escala é a escala dos nossos sentidos, é aquilo que conseguimos medir, ver, avaliar e sentir. Einstein marcou e marca a vida destes dois extraordinários cientistas. Não é o meu caso, mas gostava de partilhar convosco, e tem tudo a ver com isto, enquanto retiro a corda, um livro que li há uns anos atrás e que marcou de forma profunda, chamado Os Sonhos de Einstein. É escrito por um cientista do Instituto de Tecnologia do Massachusetts. É inspirado, é um exercício de ficção, inspirado nas notas, em muitas das notas que o professor Einstein deixou e que escrevia enquanto fazia passeios em redor, nas margens do lago Genebra. E que são o início das suas reflexões que acabariam por redundar na teoria da relatividade. Esse livro, Os Sonhos de Einstein, é um exercício totalmente especulativo em que são imaginados diversos mundos, em que a diferença essencial de um mundo para o outro, ou a característica essencial de cada um desses mundos, é a maneira como se mede o tempo e como o tempo se manifesta. Dou-vos dois exemplos. Daí perguntar o que é que estará a acontecer agora em Júpiter. Imaginem um mundo em que o tempo avança aos zigue-zagues. Não de uma forma sequencial e linear, mas sim aos zigue-zagues. Por vezes muito depressa, outras vezes muito devagar. Como é que será a vida num mundo destes? E imaginem um mundo em que o tempo é contado ao contrário, de trás para a frente. Ou um outro mundo em que o tempo anda tão devagar, tão devagar, tão devagar, que as pessoas que nascem no outono morrem antes de conhecer a primavera. Os sonhos de Einstein permitem este tipo de reflexões também. E isto tudo significa, como ficou muito evidente, quão difícil é percebermos ainda o que é que nos está a acontecer, o que é que somos, de onde vimos, para onde vamos, o que é o agora até. Não percebemos, portanto, ainda de que forma é este universo, Só esperemos que os outros sejam mais perceptíveis e inteligentes. E interrogo-me se estará o homem pronto para os avanços que aí vêm, para as descobertas que estão prestes a acontecer, que acontecem permanentemente. Se daqui a uns anos estaremos orgulhosos do progresso, qual será esse progresso? Ou, numa visão mais catastrofista, será que haverá alguém para sentir orgulho ou lamento em relação a esse progresso? O que irá acontecer aos conceitos de bem e de mal? E essa é uma dúvida permanente na espécie humana, na humanidade. A ética, precisamente, foi um dos temas que a Fundação Francisco Manuel dos Santos elegeu para um destes 5 encontros deste ano em que celebra 10 anos de existência. E isso lembra-nos que estamos no final deste ciclo ao encontro dos portugueses. A intervenção final é do Presidente do Conselho de Administração da Fundação Francisco Manuel dos Santos, Dr. Jaime Gama. Peço-vos que não abandonem os vossos lugares no final, por 2 razões. Temos uma demonstração extraordinária da teoria das cordas ao vivo, já vão perceber, e eu vou tentar fazer um número de ilusionismo. Para já, chamo ao palco para o discurso de encerramento.
Eu serei muito breve, porque o pior que há no fim de uma sessão desta natureza é haver um discurso a despropósito. Mas queria dizer-vos simples palavras. Primeiro, que a Fundação Francisco Manuel dos Santos fez 10 anos. O seu fundador foi o grande inspirador deste trabalho. E, infelizmente, aqui não pode estar presente, mas a família de Alexandre Soares dos Santos assegura com redobrada convicção o apoio a esse legado que é a programação da Fundação. Este aniversário foi a comemoração de 10 anos, mas foi um 10º ano extremamente exigente. E com os encontros que fizemos, as publicações que editamos, aquilo que marcamos na sociedade portuguesa, com tudo isso, temos a consciência de ter dado um salto em frente bastante importante. A realização desta conferência, que vai ser, para nós também, um instrumento de análise e reflexão, creio que marca um ponto diferente na maneira de comunicar ciência, de comunicar conhecimento, de pensar. E por isso nós vamos sair daqui com o estímulo dado pela vossa participação, não só pela vossa presença, mas também pela forma como reagiram a este debate. Aos que aqui vieram, aos cientistas renomados que aqui estiveram presentes e a toda a equipe, que envolve muita gente, não só da Fundação, como outras equipas que cooperam connosco, as editoras, a comunicação, neste caso especial, a TVI, e sem toda essa rede de trabalho, estes resultados não seriam possíveis. Portanto, nós partimos daqui com uma certa satisfação por aquilo que estamos a realizar, pelo contributo que estamos a dar, mas também com uma certa angústia, com uma certa interrogação, com uma certa perplexidade. Será que vamos manter este ritmo de exigência ao ponto a que conseguimos classificar esta plataforma? Pois bem, aquilo que eu vos quero dizer é que nós vamos também sair desta conferência estimulados por esta ideia de sair por um buraco negro para encontrar um universo paralelo e para reestimular a nossa energia com as cordas competitivas, disruptivas, harmónicas que possamos vir a encontrar e que estamos motivados para prosseguir. E que em 2020 vamos dar uma presença maior e melhor à sociedade portuguesa. É essa a nossa convicção. Com o vosso apoio, com o vosso estímulo, e por isso vos peço agora que, introduzidos pelo José Alberto Carvalho, possam prosseguir uma viagem no espaço e no tempo através da música, que é também uma forma insubstituível de pensamento. Muito obrigado a todos.